So next we're going to talk about creating continuity by filling in the gaps of discontinuous functions. And we're going to look at a couple of functions that are given to us algebraically. So for our first example, let's look at the piecewise function f of x given by x plus 1 for x less than 1 and negative 2x plus 4 for x greater than 1. Notice that when x is exactly equal to 1, this function is undefined because we haven't given a value right at that point. And our job is to find f of 1 so that f is continuous. So when x equals 1, we need to find out what the y value needs to be to make this function continuous. So one of the things that I might want to do is to graph this piecewise function. Notice that the first piece of our piecewise function is a function that has, it's a linear function. It has a slope of 1 and a y-intercept of 1. And we see that at the point x equals 1, if this line were to continue, we would see, I'll write this over to the side, if we're looking at just the function y equals x plus 1, and we want to know what happens when x is equal to 1, we see that y of 1 plus 1 is equal to 2, meaning that for an x value of 1, our y value is up here at 2. And that's undefined, and it's a line of slope 1 that goes through that intercept right here at y equals 1. That's for the first part of this function. Now let's look at the second piece. The second piece, I could write it over here as y equals negative 2x plus 4. I have a y-intercept of 4, and I have a slope of negative 2, so it looks something downward sloping, but we're starting where x equals 1, values greater than that, so I'm going to plug in where x equals 1 on this function, negative 2 times 1 plus 4. Notice that also gives us 2. So when x equals 1, y equals 2, and I have a slope of negative 2 continuing downward. So that's what our piecewise function looks like. The next thing that I want to do is to evaluate, well, what does that mean in terms of creating continuity? We're going to define that rigorously. We just said that, and we can know by our limit laws, the limit as x approaches 1 of our first function, x plus 1. By our limit laws, this function would give us a limit of 2, and we want to approach it from the left-hand side, so it's approaching from the negative side. Notice that that's exactly equal to the limit of our other function, negative 2x plus 4, as x approaches 1 from the positive side, coming back this way. Both those limits agree at 2, and so in order for us to make this a continuous function, it means that when we plug in 1, we would want that f of 1 value to be exactly equal to 2. Thus, so find our f of 1 so that f is continuous, we would have to write it as f of 1 is equal to 2. And that's it. Let's look at another example. For our next example, we're given the function g of x equals x squared minus 16 divided by x minus 4. And for this function, we want to know whether this function is continuous. And the only way that it wouldn't be continuous would be perhaps if it's undefined, and the domain of this is undefined if x is equal to 4. We know that because if I look at g of 4, I get 4 squared minus 16 on top, and I get 4 minus 4 in the denominator. So that means that the numerator is 16 minus 16, which is 0, and the denominator is also 0, which is an indeterminate form. So we know that when x equals 4, our function is undefined. And if our function is undefined, that means that it can't be continuous, and we're done. We're going to do one step more, though. We're going to make g continuous. And we're going to do that by plugging this hole. So how do we know what our functional value should be at 4? Because we want to be able to plug in what it should be in order to make this function continuous. The way to do that, because if I do plug in 4, I get something that's undefined. It doesn't tell me what that value is right at that point, unlike before with our piecewise function. So what could we do? We could evaluate it graphically. We could evaluate it by looking nearby. I'm going to do it by doing a little bit of algebra. And this is a preview of our next section. So g of x, I can rewrite the numerator by factoring it. It becomes x minus 4 and x plus 4 with the difference of squares. And the denominator is still x minus 4. So typically, an algebraic thing that people do would be to just cancel both these and say that the function is x plus 4. That's sloppy though, because by canceling them, it removes the discontinuity. I'm going to rewrite this function as g prime of x. By canceling the numerator and the denominator, the x minus 4 in each, I'm left with just the function x plus 4. So this is telling me if I remove this whole, I'm left with the boring function, the linear function, x plus 4. And what does that function look like? That's just a straight line. That tells us that our original function, g of x, is the line, it goes through 4, it has slope 1. And I could graph this on my calculator. This is x, y. And this is saying that on this function, just the linear function, if I plug 4 into my g prime function, I get 4 plus 4, which is equal to 8. 4, 8. Shoop! So by factoring out that discontinuity and getting this simplified function, I can see that up here when I plugged in 4, I got an indeterminate result. But when I plug in 4 into the simplified function, I see that I get a y value of 8. That tells me that if I were to add a y value of 8 when x equals 4, this function will be continuous. So I'm going to write a new function, maybe g double prime of x. It's going to be a piecewise function, and it's going to look like this old function, x squared minus 16 all over x minus 4 for x values that are not equal to 4. And then I'm going to set it equal to 8 for x equaling 4, and that will plug that discontinuity. My final example, I'm going to look at the function, another piecewise function, f of x is equal to 5x minus 2 for x values less than 2, and cx plus 1 for x values greater than or equal to 2. And we need to find c so that my function f of x is continuous. I could start by trying to graph this. I know what this line looks like, but I don't know what this line looks like because the c value is going to affect the slope of the second piece of this piecewise function. So I'm still going to graph it. Let's evaluate what happens for this line when x is exactly equal to 2 and add that to our graph. So over here, I'm graphing the line y equals 5x minus 2. So it has an intercept up here, 3, 4, 5. Oh, no, it has an intercept down here of -2, sorry, and it has a positive slope of 5. That's a pretty steep slope. Shoomp. Shoomp. And it's going to intercept a little above, oh, down here at -2. That's supposedly my straight line, and I'm going to stop it where x equals 2. So let's evaluate, what is this y value when x is equal to 2? So 5 times 2 minus 2, that gives me 10 minus 2, which is 8. So that tells me that my y value 1, 2, 3, 4, 5, 6, 7, 8. Great. It fits on my graph. So I know that this second function has to be a function. I don't know what its slope is. I do know that it has an intercept of +1, and I want it to have such a slope so that it goes right through the point 2, 8, because it needs to pick up where the other function left off. So how can I create a function that goes through the point 2, 8, and it's of the form cx plus 1. What is that saying? So over here to the side, I'm going to write, I know that I want to have a function that's given by y equals cx plus 1, and I also know that I want it to go through the point 2, 8. So I'm going to plug in the point 2, 8 into this function and solve for c. That means that y, which is equal to 8, needs to be equal to c times 2 plus 1. My x value was 2, so I plugged in for x. My y value was 8 that I plugged in for y. And now I'm going to solve for c. This tells me, let's see, I'm going to subtract 1 from both sides. I get 7 equals 2c. And I need to have a slope of 7/2. And I could have counted on the graph if I wanted to as well. So that means that this second line is going to be through the point 0, 1, that's its y-intercept, and it's going to have a crazy slope. Shoop! Ah! If I make my dot big enough, it'll take over that line, right? So this second piece of the piecewise function is going to be the line y equals 7/2 x plus 1. And really, I could have counted up. That means I'm rising 7 units and running 2 units to get up where that line took off.